Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video 29 in the series Rational Exponents and Radicals. So just to review, we discussed in previous videos what negative exponents had to mean. They had to be reciprocals, that is to say, they had to be division if all of the properties that we wanted to keep working were to keep working. In the same way now, we want to explore what it would mean to put a fraction into the exponent position. The main idea here is we want to see how that would behave, what it would mean if all the other properties of exponents that we've covered so far were to keep working. This is going to be very similar to how we derived fractions in the first several videos. Remember that we used the idea of cancellation to zero to define negatives as the thing you would add to a number to make it go to zero. And we similarly define fractions, specifically reciprocals, as the thing you would multiply by a number to make it go to 1. Now we have a property of exponents that involves multiplication. It's our power to a power property. So let's just play around with an example with a variable a in this outer exponent position. Let's say I took 3 to the 2 and raised it to the a. What would a have to be in order to give me 3? And here, of course, 3 is the same thing as 3 to the 1. Well, from the power to a power rule, we have that 3 to the 2 to the a turns into 3 to the 2 times a. And although this is a little bit beyond what we've covered so far, because 3 to the power of something is 1 to 1, we can actually equate these two parts here. But it is at least sufficient to get this answer if 2a was equal to 1. If 2a was equal to 1, then these two exponents would be the same. So without getting too hung up on the details here, how do you solve such a thing? Well, clearly, you just divide by the 2 to get rid of it and isolate the a. So that gives us our fraction. That gives us the value that we would need a to be in order to make this true. And because 3 to the 2 is 9, this means that 9 to the 1/2 power should be interpreted as 3. And in some sense, what we've seen here is that 1/2 powers are undoing second powers. But is that always the case? Does that mean that second powers and 1/2 powers are inverses of each other? Well, not exactly. Consider, for example, what would happen if we took -3 and squared it and then took the 1/2 power. Now, what would happen here is, in one sense, if I took power to a power, I should have -3 to the 1, which is -3. But is it, in fact, that I should take the inside first and do 3 squared and get 9, and then that's just +3? So this is quite a pickle, isn't it? It seems to matter the order in which we evaluate this to what value we get in the end. That's a little weird. So depending on how we're going to define fractional powers, they may not actually be functions. And we saw in a previous video that whatever the inverse of the square is, it's not going to be a function. It's going to be a relation, at least the complete inverse. What we can do to sort of simplify the story for now while we're developing this idea is to assume that our bases are non-negative, because if that's true, then there's not going to be this kind of ambiguity. To be clear, if a, the base, is greater than or equal to 0, then we will take a to the 1 over b to also be greater than or equal to 0 as well. This is called taking the principal root, and we'll talk a little bit more about that later. For now, let's just mention that it lets us define what is a to the 1 over b unambiguously, meaning without ambiguity between two values. So now if I have 9 to the 1/2 power, should this be 3 or -3? We're now going to say that it's the positive value. We're going to say it's 3 unambiguously. If your base is greater than 0, then you can always just unambiguously say that these two things, either taking the whichever order you like here because of the commutativity of multiplication, but you're going to wind up with this fractional power b over c. And cancellation will always work. If you take something and raise it to its reciprocal power, you will cancel it. This is true if a is a positive real number. So with this as your kind of starting point, copy down these critical notes, present them to me later so I know that you watched this video. If a is greater than 0, then the following things are true. A to the 1 over b to the cth power is a to the c over b. And this is the same thing as a to the c to the 1 over b power. And this is somewhat of the way that we can sort of start to decide what are fractional powers. And if I have a to the 1 over b to the b, or if I have a to the b to the 1 over b, both of these cancel and I just get a to the 1, or a. So if we restrict our domain, if we are only talking about positive bases, then reciprocal powers are the inverse of powers, and they do cancel each other. Now recall that inverses switch the roles of x and y, that is to say, they are asking opposite questions. For example, if we interchange the roles of 2 and 8 here, 2 to the third power is 8, because 2 times 2 times 2, 2 times itself 3 times, is 8. So 8 to the 1/3 power is 2, because 2 is precisely that number that if we were to multiply it by itself 3 times would give me 8. Now, sometimes to draw attention to the fact that this is a new question we could be asking, what times itself a certain number of times gives me a certain number, that we use a new notation here. We would say that x to the 1 over n is what we call the nth root of x. The nth root of x is written this way, and we use this sort of quotient looking symbol that has this little extra stick. This is called the radical symbol. This n, which indicates the blank in what times itself blank times gives me this number x, is written here, and this is called the index. This is called radical notation for this fractional exponent. You should be able to go back and forth between these two. And it is asking, again, what times itself n times gives me the number x. The second root of x happens a lot. So we usually just write this symbol, it's called the square root of x. And it really should get this extra little tail bit there. So again, critical notes, copy this. This is the radical notation for fractional exponents. A to the 1 over b is the same as the bth root of a. And in particular, a to the 1/2 power is written this way and is called the square root of a. For example, the 4th root of 81 is the same thing as the 1/4 power of 81, and this is 3, because 3 times itself 4 times will give me 81. Now let's note one more thing, which is that when the index of the radical is odd, or when we're dealing with an odd denominator, we can sort of relax our concerns about the base being negative or positive. And this is because if we have an odd number of negatives, we'll get a negative in the end. And if I have an odd number of terms, only if they're all negative will I get this negative if they're all going to match. So in other words, what is the 1/3 power, or the cube root? This could also be written with radical notation, and this happens frequently enough to get its own name. This is called the cube root. The cube root of -27, or the 1/3 power of -27, is -3. And that's because there's only this one number, -3, that if I multiply it by itself 3 times, I get -27. No other number has this property, so the answer is sort of unambiguously defined. Okay, here is your praxis exercises for the day. This is what I want you to know how to do with fractional exponents and radicals for now. We're going to be doing more with them, but for now, I want you to know how to simplify expressions that look like number 1, write things in radical form that are in exponential form, write things in exponential form that are in radical form, and evaluate things that have nice answers to them. And I assure you, all the things in number 4 have nice answers. So pause the video at this time. Okay, let's see how you did. So for number 1, the main idea here is that we want to sort of group the like bases together. There's A's, B's, and C's in the top and bottom. And there's also this 1/10 power up top. Power to a power will be the product of powers, and the quotient of two like bases will be the difference of those powers. We can also begin by changing where the negatives are. I like doing it this way because this helps me sort of get rid of a few of the double negatives that occur. If I move this to the bottom, it becomes positive 4/7. If I move this a to the -1/3 to the top, it becomes positive 1/3. Now I'm going to combine these bases. So a to the 2/3 times a to the 1/3. Well, the product of like bases is the sum, and 2/3 plus 1/3 is 1. And the product of these is their sum. And 3 plus 4 is 7, so this is 7/7 or 1. You can reduce these fractions. Now, the 1/10 power on the outside, oh, and then C, of course, right? C is the 3/5 power up top and a 1/5 power on the bottom. Quotient of powers is their difference, so I subtract them, I get 2/5. Now we bring the 1/10 in and multiply them by all three of these exponents, and we get a to the 1/10, b to the 1/10, and c to the 2/50ths. 2/50ths reduces to 1/25th, and this is our final answer. Now, to get this into the right form, what you could do is first rewrite it as x to the 4th to the 1/5, sort of separating the numerator and denominator. Remember, writing 4/5, or any fraction for that matter, as its numerator times 1 over the denominator is a nice trick, because then we could see times as coming from raising a power to a power, and then this inside part here is getting 1/5 powered. The 1/5 power is what I want to rewrite in radical notation. So here we have it. That's the 5th root. Here in radical notation, I've given you a little bit of a trick because this guy's hiding out on the bottom. Now, we could sort of reverse this kind of step above to write this as x to the 5th to the 1/2 power, which is just x to the 5/2, and 1 over something to a positive power. Well, this is the same as -1 of that thing, right? This is the reciprocal. Or you could just imagine moving this to the top and changing its sign to negative. If you want to take that shortcut, that's fine. But this is going to be x to the -5/2 power. That's what this guy here means. Okay, let's evaluate some of these. What is the square root of 25? Well, 5 times 5 is 25. Now, it is true that -5 times -5 is also 25. This positive answer here is called the principal root. And usually when you see a radical, like radical 25 or the square root of 25, what they're asking for is the principal root. They're not asking for the complete set of roots. All roots of 25 would be second roots of 25 would be 5 and -5. And this is because -5 times -5 also works. It also gives you 25. But when they just ask for something like this, when they just ask for radical 25, they're usually not asking for that second negative answer. When they want that negative answer, usually they'll put a plus and minus up front and say, what's this? And then you give both answers. We will cover this quite a bit more when we talk about the quadratic formula, and we might even see it a little bit when we talk about complex numbers, which will come up at the end of this section. But for right now, when you see a radical, an even-rooted radical, or an even-indexed radical like this, you should just give the positive answer that it corresponds to. Here we have sort of a less ambiguous kind of situation because I'm asking for the cube root of -125. There's only one number that sort of does this, and that's -5. I want this to look a little bit more like a -5. There we go. So -5 times itself 3 times gives you -125, and only this number has this property. There are no other numbers, well, no other real numbers, that if I multiply them by themselves, this 3 times will give me -125. How about this one? Again, we're asking for the principal root, right? If they give you just a simple, what is 625 to the 1/4 power, they want the positive answer, and I am looking for the positive answer here. But the astute among you will probably note that this is exactly the same situation as before with the square root, because -5 turns positive in pairs, and so 4 of them is also 625. Don't worry about that too much. We will talk about this more as we go. However, let's keep in mind here this sort of new terminology. This is called the principal root, and it's the positive answer to this question. And really, that's what I'm looking for in your practice exercises when you show me this work later. So here's some things you might have noticed. Let me do just a really brief wrap-up. You might have noticed that this numerator just comes inside as an integer power, and this denominator becomes the index of the radical. You may also notice that 1 over radicals turns into negative exponents in the same way. If you want to use these as sort of shortcut properties, that's fine, but you should also know why they work from our previous properties. All right, that's it for today's video. Thank you for your patience and have a great day. I'll see you in the next one. Good luck with your studies.